Good evening. It is my pleasure to warmly welcome back all of you for the workshop on soft robotics. Yet another splendid chapter of EECon 2021. To chair the workshop of EECon 2021, I invite our workshop session chair, Director, Center for Advanced Robotics, Dr. Damit Chaturanga, and the program chair of EECon 2021, Senior Lecturer of University of Moratuwa, Dr. W.D. Prasad. Yes, sir. Please carry on with the proceedings.
Thank you, Ravi. A warm welcome to all of you today. So we will be having our first workshop in EECon, collaborated by the ESOC Society and Center for Advanced Robotics with the help of IEEE RAS Sri Lanka section. And today's workshop, we would like to focus on soft robotics for biomedical applications. Why we need soft robotics? It's a topic these days. Even with the corona epidemic, you could see that the health sector, the services sector, faces quite a lot of shortage in manpower. And we, as robotics enthusiasts, like to solve these problems using high-tech solutions in the robotics research. So for us to learn more about these new trends in technology, we wanted to invite prominent researchers, leaders in this robotics in biomedical applications to this workshop. And today, two of our leaders in the have come and joined with us, and Professor Thrishantha Nanayakkara and Dr. Thilina Lalitharatne from Imperial College. And we would like to warmly welcome you and the spectators or the listeners for this workshop. And without spending more time, we will move on to the workshop. So today we will be in our discuss delivering speeches 40 to 50, 45 minutes of their research, and following that speech, we will be having a small 15-minute Viva session. For the Viva, not Viva session, a Q&A session, and the questions can be posted in the chats, and I will be asking the questions directly from the speakers, and hope that will help with the situation, the workshop. And without further ado, I would like to call Professor Thrishantha Nanayakkara of Imperial College to deliver his a soft robotic approach to understand how the brain organizes the body to make real-time survival in natural environments more efficient. So without taking much time, I would like to introduce the speaker, Professor Thrishantha Nanayakkara, a senior member of the IEEE, received the BSc in electrical from Moratuwa in 1996, and MSc degree in electrical engineering and PhD degree in robotics from Saga University, Japan in 1998 and 2001 respectively. He was a postdoctoral research fellow with the Department of Biomedical Engineering, Johns Hopkins University, Baltimore, USA from 2001 to 2003. A senior lecturer with the Faculty of Engineering, University of a fellow with the Harvard University, Cambridge from 2008 to 2009. A research affiliate with the Massachusetts Institute of Technology, Cambridge, USA from 2008 to 2009. And a senior lecturer with the Department of Informatics, King's College, London, from 2012 to 2016. He is currently a professor with the Dyson School of Engineering in College. Co-authored 2 textbooks and more than 150 peer-reviewed papers. His research interests include soft robotics and robot interaction with certain environments. So I would like to invite Professor Thrishantha to deliver your speech, and I hope that everyone will enjoy the presentation. Over to you, sir.
Thank you, Damit. Can you hear me clearly?
Yes, we can hear you.
Okay, so let me share my screen. Can you see my slides?
Yes.
Okay, so is it full screen now?
Yes, it is.
All right, great. Thank you. Thank you very much, Damit, for inviting me to give this talk. It's a great pleasure to be with the University of Moratuwa community, especially with the robotics, to see how the robotics has grown in University of Moratuwa. So it has always been a pleasure to be with you. So I'm going to talk about the soft robotics approach to understand embodied intelligence, which is slightly different from what I sent you, Damit. So I'm the director of the MORPH Lab, Dyson School of Design Engineering at Imperial College London. And also sharing. So just to give a quick introduction to the Robotics Forum. We formed in 2015 as a bottom-up initiative, and it has been recognized as an Imperial College Network Excellence in 2018, and we have 44 robotics laboratories. That means 44 principal investigators. I am one of them. And then we have more than 200 PhD students at the moment, and we have secured more than 50 million pounds of funding, and then currently the ongoing funding is about 50 million pounds. It can be 60 million pounds currently ongoing. And then we have 16 patents and 15 commercial. It has to be updated. Is 16 commercially exploited. That means 16 companies spun out from the forum. And then we have more than 2,400 publications. So just to give you some idea of some of the labs, I'm not talking about all 44 labs. Is George Milnes working on soft robotic, endo endoscopic robots, where you can have soft robotic anchoring in the intestines, mostly in the gastrointestinal tract, to do surgery. And then Ferdinando Baena, so he's developing robotic minimally invasive surgical tools that can go into the brain to do brain surgery, which is inspired by mosquito sting. And then Mirko Koak developing micro robots inspired by bees, and then YT working on dragonfly inspired robots and the vision. Etienne working on action, and Nicholas Rojas working on soft robotic grasping, and then my lab working on soft robotic patience and grasping and interaction. So right now I'm the chair of the Imperial Forum. It has been an honor to lead this forum so far. Okay. So just to give a background about how it came to soft robotics, like it used to be very rigid robots in the industries, doing very precision control, like car assembly and that kind of things. Like, so you cannot see any humans in that because this kind of segregated, right? So the robots and the humans. So the robot area is a no-go zone for humans because it's too dangerous. And then these robots need very calibrated spaces to do something. And then if even something goes like about a millimeter off, whole operation collapses. So that was 1980s robot. And then we have oops. something happened. Let me wait. Yeah, I'll keep talking. So this kind of robots were very like bulky and rigid, and then you cannot really go near them. So it is very important to have make advances in human robot interaction, because like you cannot replace humans 100%. So you need to have robotic. So try to kill this. Oops. Something got stuck. Sorry, I'm trying to stop sharing. Sorry about this. Okay. Sorry, Damit, about this. There's
Sorry,
something
sorry,
happening.
just continue. Maybe it will turn on.
Yeah.
Stuck, I guess.
Okay, so looks like it is.
Would it be possible to restart the?
Yeah, I will do that. I'll do the restart the computer. This never happens usually. I don't know why. Maybe I'm on Zoom and then something happened on the Wi-Fi.
Maybe if you can turn off the camera, and maybe that might help a little bit.
Yeah, okay. Okay, give me a couple of seconds.
Sure. Sorry for the we're having some technical difficulties, but please do bear with us for some time until we get this sorted out. Please do bear with us for a few minutes until we sort out this technical difficulty.
Damit. I
Okay.
can
Yes,
try,
you can
or
now.
we can go.
Okay.
You can hear me?
I can hear you, and you can share the screen now.
Let me try again. If that doesn't work out, like let's go with Thilina, and then I will.
Okay.
Can you see my screen?
Yes.
Okay, so where were we? We were right. So here. So if this doesn't work out somehow, like we will go ahead with. So then the collaborative robots came into being, like in late 2000, and then so the good thing about collaborative robots is that you could have humans working side by side with them, right? Um, like this. So these collaborative robots are safe to be around humans, and then you can see, like, now humans are working along with them. So this is a big development. So these robots are RS universal robots, and then as these collaborate. So these are called cobots, right? So we call them, like, these new kind of robots, the cobots. So it's a step towards a soft robots, right? Uh, okay, so now I have to be careful about slide transition. Okay. So these cobots usually have this kind of
Advantages of SEAs are that the applied force can be precisely controlled, and the shock tolerance and compliance with the environment can be increased.
have serial elastic
SEAs are
actuators,
used in
right?
a variety of
So
robotic controllers.
they can
UT
be
Maestro hand
they can be
exoskeleton
compliant,
is a
and then
device that provides a
it is
system
safe
movement
to work around it.
advantages of SEAs.
So, and then came these kind of soft robots inspired mostly by natural animals like octopus. So these are completely soft robots.
To mimic this ability, Lasky's team
Right.
used coils of wire
So this is
inside
Cecilia
some of the
Lash's
robot's
group
arms
working
made
on
from
octopus-inspired robots.
To mimic this ability,
So it is
Lasky's
very
team used coils of wire
like
inside
very
some of the
soft,
octobot's
and
arms
no
made from a
bones
material
involved,
called
and
sheet
then
memory
these can
alloy.
be used
When
in
current passes through a
surgical
coil, it
robotics.
heats up
For
and takes a
example,
certain
it can
weight from
go
its
through a
sheet.
narrow trocar port
Sending
into
current
the
through
body,
different combinations of
and then
coils
do
allows the
some
robot's
surgery,
arms to bend and
a
flex
useful
in all
task,
sorts of
and then
ways.
get out of the body. And even if they collide with a soft tissue, it doesn't make any damage, right? So this is a project I was involved in, and then this is Wyss Institute Harvard robot that is more underwater robotic applications. Uh, yeah. So now there are a number of soft robotic applications in the industry. So grasping and picking and placing and rehabilitation and that kind of. So the soft robotics market is growing roughly at about 40% compound annual growth rate. And then now it is about $783 million market. And it is projected to be, exceeding a couple of $1 billion by 2024. So it is rapidly growing, and then there's so many opportunities, and then lots of research funding available. So, okay, about my talk today. I'm using soft robots to understand how a living being survives in a natural environment, right? So we have a brain, we have muscles, and we have bones, right? So the conventional thinking was that the brain takes care of all the intelligence and six brain, and then brain does the computation, and then the body is just a receiver of the brain's commands. But now that thinking is gradually shifting, and then we are pushing those kind of frontiers, and then we are discovering that not only the brain, but also the bones, and then the joints, the cam profiles, and then the exact shapes of these musculoskeletal systems are also solving problems, and then they are also computing uh, uh, to solve problems. So to just to give you perspective, so the environment presents us with uncertain states, and then it also is the source of energy for us, right? And then if the uncertainty of the states of the environment, for example, you are riding a bicycle on a bumpy terrain, if that environment is very highly uncertain, it the brain cannot deal with that kind of things, because the brain works with models, and we call them forward models, and then it uses model based control, predictive control. But when the environment is very uncertain, the uncertainty is high, these model based controllers fail. So what then it does is to take control over the tuning the stiffness of the muscles. For example, if you're riding a bicycle on a bumpy terrain, the brain would ask you to come off the seat and then ride the bicycle with bent knees, right? So then the bent knee is done using co-contraction of thigh muscles, and then it tunes the knee joint as a like a mechanical filter, right? So that mechanical filter, the cutoff frequency of that mechanical filter can be shifted by changing the stiffness of the knee joint and the angle of the knee joint, right? So I'll talk about that later. So brain is now making conditioning the body to behave like a mechanical filter by co-contracting muscles to solve a problem that it cannot solve using model-based control, right? But when you co-contract muscles, it requires a lot of energy, right? So the price it pays is a high energy solution to deal with uncertain states, right? But if it is fairly like uncertain, but like it is the models fairly work, and then it takes this medium energy approach of using model based controllers with predictive control. But there are certain things that are really predictable in the baseline activity of the environment. It happens all the time. For example, you're walking, or you're grabbing something, and then the reaching movements, they happen all the time, right? So there's no uncertainty in that. So when you swing the leg, when you're walking, it is a swing leg, doesn't come into contact with anything. So those are repetitive tasks. Like, so for that kind of things, it doesn't require energy to have the right cam profiles in the bones and the joints, right? So this evolution happens in the background to deal with very baseline activity. So this is how I frame this whole problem. So the evolution happens by evolving the brain, the muscles, and then the shape of the cam profiles to deal with this kind of a space in uncertain world. Um, so to give the spectrum in a different sense, like, so we have bodily computers, pure bodily computers. For example, like you have the ear, and then this catchment area is like a funnel, and then that helps you to concentrate pressure to the eardrum, and then there's this mechanical amplifier, and then it vibrates a helic, like a spray, the spiral, conical shape spiral, right? So it is when you have a tapered tube, and then when you vibrate a liquid in a tapered tube, what happens is all the frequency components get separated along the tapered tube, and then you know exactly what frequency component is going to be where, right? and then the cochlear hair picks up these frequency components. It's like a Fourier series done in a tube. And then it informs the brain in the frequency domain. So that you get time domain signals coming in, and then it is real time converted to their frequency components, and then inform the brain in the frequency domain. The frequency features sent to the brain, and then you can really use model-based controllers to do real-time hearing. Otherwise, if you send time domain waves to the brain, and then if the brain were to do the frequency separation, it is taking time, and then your hearing won't be real time. So that those kind of computers are there all over the body, right? And then the other extreme is the brain model-based controllers. The synaptic plasticity of the brain helps to build models, and then in between is the control I mentioned, like tuning the body shape of real time to deal with that kind of environments. So soft robotics help us to understand this kind of things that we can test. For example, my PhD students are Goma. She graduated a couple years ago. She studied how goats survive on mountain cliffs, right? So mountain goats. So the secret is in the last leg, how do they sleep when they walk? And when they sleep, your brain can know about after about 120. It takes about 120 milliseconds to reach the signal to the hoof, or the dynamics analysis of the hoof, and then experimentally showed that the hoof is more like, just like the eardrum, and then the cochlea was solving the real-time hearing problem. This hoof is solving the real-time sleep reduction problem, right? So that is her PhD. So this is, I'm not going to details, like, so she did very careful mathematical analysis and then did experiments, and then this is her final finding. You have consequences in the yaw, roll, and pitch. In the hoof, the color represents the how much energy is required to push this hoof against the surface. If the energy is high, that means like it is harder to slip, right? So it is, you might wonder, okay, what the friction coefficient is doing. Friction coefficient is in the baseline, but that is not the point. So the compliance in the joints help dynamically break than just the kinetic friction coefficient, right? So and the slip and stick and behavior due to the correct index in the hoof is helping the hoof to break on this kind of slippery things. So you can see the details in IEEE Translation Robotics, this paper, more details. So it is very interesting to see that, like, the goat is using that hoof, but like we don't have that kind of hoof. But if you have seen the ice skaters, how they slip, stop slippage on ice, they implement a goat hoof using the hip joint, the knee joint, and the ankle joint. It is a dynamic solution to slip reduction or braking on ice, right? So this is the behavioral convergence to the same solution, the evolution solved in the hoof mountain goat. It's interesting to see that, right? So the important point to notice that the friction coefficient didn't change. It's just that there are dynamics that problem. So the point is we can use soft robots and then carefully controlled soft robots to understand that kind of phenomena. And in this case, like, so you should just notice that there's no sensor involved, there's no computing involved. Purely the computing is done by the hoof, mechanics of the hoof, just the springs and the bones. There's no thinking, there's no processing, there's no algorithms running. The algorithm is the mechanical structure itself. Um, and then Ella Mohammed, she just graduated a couple of months ago. So her PhD is about understanding the angle-dependent damper in the cam profile of the knee joint, and then um, uh, how that determines the efficiency of walking, right? So her hypothesis is that, so we have in the knee joint based on, because of that special cam profile, we have an angle dependent damper in the knee joint, right? So when you walk, our angle, knee joint angle varies from about 10 to 30 degrees, and then that causes a damper change in that knee joint. So her hypothesis was that, okay, so this angle dependent damper profile is something like and then what need to have that to do efficient locomotion, right? So she approximated that with a hyperbolic angle dependent damping profile, and then she looked at a index called the coefficient of variation, which is how much variation noise you get in the collision force when you walk, divided by the expected value of the collision forces. That means like you have lower collision force and then reduced noise in the collision force, and then the angle speed and then angle variation during locomotion. So she did experiments using a soft robotic equivalent of the knee joint. So she implemented the knee joint using a backdrivable motor and then got a ground to collide with that knee joint, right? So what she saw was that, so depending on the slope of that angle-dependent damper, so the peak collision force changes. So the peak collision force reduces when you have the right angle dependent damping profile. And then uh, the important thing to notice is that not only the collision force reduces, like so when you walk, uh, you feel less pain due to collision, right? So you know when you have the swing phase and then your foot collides with the ground, your body doesn't shake as much when you have that correct knee joint angle dependent damper, and then it reduces to a very minimum level compared to a fixed damper at the knee joint, right? So just imagine a fixed damper is something like friction in a pivot joint, right? But when you have friction in an angle dependent damper, the collision force reduces. Not only that, the variation of collision force also reduces. So this is called entropy in the environment reduces. So this is important because when the entropy reduces, the brain finds it easier to model the environment, right? So if it is a high entropy environment, it is very difficult to model that environment. You need more neurons to model that, and even that it is not very accurate. And this is really helping. So the knee joint angle dependent damper evolved to solve an entropy reduction problem as well as a collision force reduction problem. And in that way, your walking becomes very efficient. So that is her finding. So another simple example, so he graduated, he finished the PhD last month. And so his work was a collaboration with the Shishou Central Hospital in China. And then they had a big problem of like Shishou Central Hospital serves about um, 200,000 farmers in that area. So, you know, those farmers get very frequent wrist problems due to excessive work, maybe. And then they need orthosis, right? So this kind of restrictive orthosis. But the problem with orthosis is like we have the orthosis go home and then they complain about pressure point developments is uncomfortable. And so we developed a soft sensor skin that can go under the pressure, the orthosis, so that the hospital can monitor pressure point developments remotely, and then even maybe release it. We didn't do that, but like the future step is to remotely release these pressure points by sending a command to a local coil that can warm up the plastic, and then it can, you know, this very low melting point thermoplastics, and then that can release that pressure. So we haven't done that yet, but like so that's the aim. So the important point is like, you know, just these sensors, when you wear them skin, there's a lot of, right, you know, friction and shear forces, and then moving around the hand, and then that can cause noisy signals, right? So the entropy of the signals is very high, and which is not going to be helpful to the hospital. So we rather than solving it using very complicated processes, solve that using a morphological approach by taking, noticing that this fish scale type patterns uh, help us to spread stresses to larger diameter scales, and then leaving the smaller diameter more stiff. Basically, it is a stiff gradient, right? A stiffness gradient. And then the more compliant areas take the stresses, or stress concentration is higher than the more stiffer area. So we, around the sensor, we have a stiffer area, and then that insulates the sensor from environmental disturbances. So this way, very simply, by designing the morphology, the physical design, we solve the problem of noise reduction in the sensor. So it is just like the knee joint the environmental noise to the brain, or the hoof or the mountain goat solving the slippage problem, or the ear cochlea solving the real-time hearing problem. The physical computers solve that kind of real-time signal processing problems. That's the whole point. Um, and Damit's work, some long time ago, so our collaboration when he was with Shinichi Hirai, and then he came to my lab, and he did some nice work with a soft robotic finger. The idea is like, so you have a permanent magnet and then some Hall effect sensors around it, and when you rub against something, the way the Hall effect sensors, the relative distance between the Hall effect sensor and the permanent magnet, how they move around can be taken, uh, viewed as a covariance matrix that changes, or kind of the specificity of that rubbing against that a surface can be enlarged by having different covariant matrices in that space. That way we can distinguish very look-alike surfaces. So it is a morphological solution to something that cannot be solved easily using signal processing alone. Another example from Hadi Sadati, a wonderful PhD student some time back. This is about active Velcro, right? So active Velcro is where the Velcro is installed by hooks in some ants, and then you always Velcros in bags and things like that. So the idea is slightly different here, which is active Velcro. So with the shape memory alloy, you can change the temperature, and then you can even soften the Velcro or stiffen the Velcro. That way you change the complete behavior of the Velcro. So this is like, you have a mechanical solution to a complicated problem, but like then you can condition the mechanical parameters here, the stiffness of the Velcro, to change the behavior of that mechanical structure. Um, I will maybe skip this. So this is about uh, I will talk a little more about the conditioning of the body. So we view this as a recursive estimation problem. And then the important thing is like, so you have a random variable to be estimated, which can be, for example, in a GP. When you go to a GP, they would examine your abdomen, and then they have in their tactile fingers, they feel something in your abdomen, and then it is a random variable. For example, it can be the stiffness of intestine, or from the rib cage to the lower edge of the liver, if it is a swollen liver or not, and that kind of those are all random variables. And then the perception of those random variables has to converge rapidly to get a good diagnosis, right? So if it is an amateur, like a first year medical student, they will feel these random variables all over the place. But a trained GP would clearly feel these random variables, because they know how to condition their fingers, stiffen, or the shape of the fingers, and then placing them with the right force and all these things. So we are working with medics in the medical school to develop a patient with that, so we can quantify examination behaviors and then compare junior medics versus senior medics, and then inform them how to improve their examination behaviors using a mathematical formulation of recursive estimation formulation. um, I'm not going to go into details of that. So it is basically what is happening is like, so we have some random variables to be estimated, and then we can take control over the light function of the perception, which is the sigma, the variance of these random variables. Let's say haptic perception, visual perception, or auditory perception, right? So when they examine, they use all these sources. So here they might feel, and then they might tap into the body, and then they might get acoustic feedback, auditory feedback, hearing how it sounds like, or they can take visual feedback by pressing the body and then watching the face of the patient, which I think Thilina will talk more about it. And then just using the pain expressions in the face, they can estimate these random variables, right? So then there's a sensor integration process. Then the challenge is how to teach medical students to do this multi-modal integration very fast, right? Uh, and so in mathematical sense, like what it means is, for example, our sensors are part of the muscles, right? So our sensor, the force sensor, is serially connected to the muscle, and then the spindle sensors that are giving you the perception of the joint angle and then the speed of the joints are also part of the muscles, right? And then when you feel a random variable, let's say this dotted line, if it is noisy, you cannot think about it, and all you can do is um, to stiffen this muscle or contract that muscle to condition these sensors a little bit more sensors. And then say by doing that, you feel the random variable in this light blue curve. Now it is slightly sharper, and then going from this dotted line to this sharper light blue line is like a probability density function, going from this probability to that. This random variable, given some zeta, is stiffness parameters of the fingers, and phi is a behavioral set of parameters like the force control or the movement control, right? So they can take two actions: movement control or force control, phi, and then stiffness control of the fingers. And then now we are telling the, showing the medical students how to control these movements or forces and the stiffness of the fingers to rapidly change this function to that function, right? And which is called the information gain or Kullback-Leibler divergence. So this is a collaboration. I'm leading this project from Imperial College London, and my collaborators are coming from University of Oxford, Radcliffe Hospital, and the University of Cambridge as our partners. So we test this kind of hypothesis. We cannot test it in a human finger, so we make a robotic finger, and then we control the stiffness of this robotic finger, and then we simulate tendon feedback using force sensors, and actually the flips in other capacities. Then we prove the hypothesis that the likelihood function can be conditioned. Likelihood function in a recursive estimation process can be conditioned. The shape of that can be conditioned just by controlling the stiffness of the finger. And in that way, we show that the recursive estimation process can converge to the true state with a very minimal number of. So I will. How am I? How many minutes left?
So you have about 10 minutes more.
10 minutes more. Okay.
Yeah.
So we are extending this robotic.
Violambita. Yeah. Martin Hafiliga.
So the controller to have a soft robotic patient that can camouflage a real patient, right? So this inspiration is coming from the octopus. For example, you can see this octopus first, and then it camouflages itself to a seaweed, right? Quickly. So the idea is like, let's say you have a real patient, and then we have some data coming from the abdomen of the real patient, and then let's say this patient is at home, and then we can wear some kind of a jacket to estimate the internal organ conditions of the patient, and then we can send these physical parameters to a hospital where you have a robotic patient, right? So the patient is at home, and then we physically project the real patient's internal organ conditions to a robotic organ condition in the hospital, so that the doctors can go and examine the robotic patient, which is now trying to camouflage the real patient at home. So it is a physical twin of the real patient. And then the doctors take examination decisions based on their examinations of the robotic equivalent, which not the real patient. That way, a lot of patients don't have to come to the hospital, and then we can reduce NHS hospital congestion. So this is something we are developing these days. I think I'll stop here and give it to Thilina to talk more about the robotic patient development, and we are doing a very extensive, FEM simulations to develop a soft robotic, no, sorry, a surrogate model of organs, and we have taken the MRI scans from real organs of humans, patients, and then we know now how to train deep neural networks to simulate this, force interaction conditions with real organs, and then we are making a digital twin of the real human body, so that you can haptically interact with that and in a virtual reality environment, and even we can project those um, in virtual computations to a real physical body, so that like when you examine the real physical robotic abdomen, you can also get a visual feedback of how the underlying organs might be feeling your forces. So this is an ongoing work. I think we have 2 more years to finish this project. So we'll have more exciting things next year, hopefully. So I'll leave it to Thilina to talk more about it. Maybe I will talk quickly about this slide. So this, we are working on artificial evolution. So the like, when the brain gives commands to the muscles and joints to condition them, like I said, like the GP would control the stiffness of the joints, and then in this case the monkeys, when they have to travel with something in the hands, they have to go bipedal, very called episodic bipedalism. For a brief time, they have to do bipedal walking, and then those brief bipedal episodes contain information for physical evolution, right? So mathematically, what it means is, you can, let's say, in an inverted pendulum case, a controller can control the inverted pendulum, and then if there's the joint that has, like, to stabilize that inner pendulum, but the joint can locally monitor what the remote, or the brain, for example, trying to implement, right? So, and then it by pushing and pulling, it is trying to a spring and a damper, and then this local joint gradually develops a spring and a damper, and then watches how the brain withdraws its function, right? And then what she saw, Saina saw, was that ultimately the local adaptation and then the central brain, they settle down to a solution that either of them cannot accomplish on their own, right? So there's so the physical adaptation doesn't take to overtake what the brain is doing, but A physical adaptation is trying to come to a certain solution that simplifies the task to the brain. So that's some ongoing work. Our hypothesis about um, how the brain and then the physical body evolves together, right? So you can read more on IEEE Access. I'll finish with that, and thank you very much for having me for this talk.
Thank you very much, sir. Professor Nanayakkara, if you have a audience, if you have any questions, feel free to take this time to ask these questions. Either you can put it on the chat, or you can allow you to let you speak. Okay, so I have a few questions now. You have said about multimodal integration and this, finding out the random variables in certain palpation and activities regarding robotic applications. Now, suppose that we are to make a robot using some of the theories. Would it be easy for us to train maybe in terms of artificial intelligence to train some robots in these finding out these random variables or these multimodal integrations? Would it be possible for us to train a system like that with the current knowledge that we have?
Yeah, of course. So our approach is to get the robot to do it first, and then we learn from it, and then we involve him. So like it is happening in two ways. Basically, we get the Thilina will explain it more how he uses these robotic interventions to augment human behavior. Um, so we can really take a purely a robotic learning approach, and then robot learns first. Like so, I showed that robotic finger, trying to learn how to locate a nodule in a soft tissue, which is purely haptic, right? But if he had visual perception from the robot, and then the robot could also hear, there's multimodal integration, and then we can see what kind of cost functions or reward functions will guide to a learning solution, and then that way we can understand how the humans be learning it, and then inform training methods. Like so, our primary target is to discover a set of teaching methods to medical students to improve their medical training using a approach. So because like people have been trying different ways to teach medical students, there are so many theories about medical training, medical education, or whatever, and then we really don't know how to validate them. So we are taking a robotic approach, like so the totally a robot trying to do the same thing, and then that way we learn how to do it better, and then we inform the medics about it. So it is a robot inspired biology than bio inspired robot. So it's, our approach is yeah, it can be done.
Then my final question for you would be, how would Sri Lanka benefit from research like this in the near future? That is one of the main important questions I would say people have.
I mean, this is a very important question. So I would say Sri Lanka can benefit immensely from this kind of. I mean, I can just off the cuff, I can say Sri Lanka has in a shallow waters, right? So all around Sri Lanka, right? And then there's so much tourism going on just about the marine resources, right? Diving and underwater scenery, shipwrecks, and then there's so much seaweed and sea I think resources other than fishing, and then there can be the soft robotic marine robotic solutions that can harvest resources or to promote tourism or guide tourism, or like just let's say get somebody, a tourist who can enjoy underwater sceneries in a virtual reality environment from a hotel, for example, or from another country. Just they pay some subscription. So to enjoy Sri Lankan things using a robotic intervention, right, and mediation. So due to COVID, there was a lot of reduction in tourist travels. But in the future, you can have robotic mediated tourism in like maybe in experience in underwater sceneries. I'm working with a Sri Lankan travel company. Just initial thing. They are specializing in shipwrecks. Then we are thinking of some kind of remotely controlled robotic intervention to give a remote experience to tourists, and that way we get subscription money from tourists and that kind of things. Or it can be in agriculture, right? So in agriculture you have, I think I if I'm right, you don't have people now to climb up coconut trees, right? Pluck coconut. So it's not a difficult problem to find a robotic solution to climb up, and then just like GP was doing to understand the abdominal condition, you can have a soft robotic intervention, estimate whether this coconut is ripe or not, before plucking. Like, you can knock on it, or you can have visual feedback, you can have haptic feedback, you have auditory feedback, just knock on it. It's multimodal integration, right? Real time. And then maybe you can have an app so that somebody can interfere with that and then take a decision to pluck these coconuts, and then that is another solution. So in the medical industry, there's massive intervention. I think the thing is, like, in medical industry, it's very expensive to do that, right? So I think rather than trying to do very costly things in Sri Lanka, my suggestion is, given the limited, like, for just to give you an idea, like, so my RoboPatient project alone is a 1.8 million pound project, right? And then of my project budget is in 1 million pounds, which is about like 300 million rupees. I think Sri Lanka should invest that kind of money on a single project, right? So here we are okay, right? So in UK, so our budget is like several billion pounds research funding and per annum, and then which is fine, right? So in Sri Lanka, because the budget is limited, you should use that limited budget to solve very urgent industry problems. I would say agriculture, or tourism, and then that can kind of benefit them. And then don't rush to solve problems that can be solved by other people. And in the university, maybe if you do projects that takes about 3 to 5 years, and but take a fundamental theoretical approach. But if you break that theoretical barrier, then there are so many opportunities out there. The mistake some people, I think, are doing is, like, they are trying to do very quick things and quick fixes, and then 3 month, 2 month, like, so people will come and tell you, okay, so I need that solution in 2 months. You should ask them to go to another place, like, not the university. The university should be solving problems that might be getting results in about 3 or 5 years. But if you continuously do that, at any given time you have results from things you started about 5 years ago, right? And then you will stay on top. So that is what we are doing. So our horizon is about 5 to 10 years, and then, but at any given time we have solutions coming from what we started about 10 years ago. And every day there's a spin out company or something coming out, but it is coming out as a result of something started 10 years ago. So that's my advice.
Thank you very much, sir. That's a very good explanation of how we can help with Sri Lanka. More from the audience asking, do you think that the biomimetic will be future trend in robotics?
I don't think so. Biomimetic is a wrong way to go. Like, biomimetic assumes that we know the biology, right? So like to mimic, you should know what is happening in biology. So we don't take that approach. We take robot inspired biology. Like, so we take a hypothesis about what the biology might be doing and then test it in a robot and then understand what is happening in the biology, right? So the old approach is like we think, oh yeah, I know what is happening in an owl wing, and then I'm trying to make a owl wing, a robotic owl wing inspired by the real owl, and then you end up doing the wrong thing, right? Because you assumed that you know what is happening in the owl wing, and then which is wrong, right? So your assumption is not the fact, right? So it is very important to assume that you don't know what is happening in the biology and then test it, like in either on the biology or in a robotic approach. So we take um, uh, not biomimetic, it is robot inspired biology, or you could say bio inspired robotics, like, so which is the closest thing. Which is not really even bio-inspired robots. So we are taking a robot-inspired biology approach.
Right. Thank you very much, sir. And is there any other questions that the audience needs to answer? You can ask questions straight away if you like. All right, sir. So thank you very much, sir. That's I see. I see. I don't see any other questions from the audience. So thank you very much, sir, for your kind lecture and taking time for us. Oh, there is another. Sorry. Yes, thank you very much, sir. And there's applause from the audience. Thank you very much for your you spending time, valuable time, to deliver this speech. And I would like to thank you and invite the next speaker, Dr. Thilina Lalitharatne, to give his speech. And to introduce Dr. Thilina Lalitharatne, he is a member of IEEE and received BSc Honours in Mechanical Engineering and MSc in Electronics and Automation at the University of Moratuwa, Sri Lanka in either year 2009 and 2019, and her PhD degree in Robotics and Intelligent Systems from Osaka University, Japan in 2014. From 2015 to 2019, he was a senior lecturer in the Department of Mechanical Engineering, University of Moratuwa, and he is now currently a postdoctoral research associate in the Morph Lab, Dyson School of Engineering, Imperial College London, and a visiting researcher at Bio-Inspired Robotics Lab, University of Cambridge. His awards and honors include BCI Award and the first place winner award in International Brain Machine Interface Hackathons at SMC 2017 conference and BIBE 2019 conference respectively. He has published more than 50 peer-reviewed papers, and his research interests include human-machine interaction, soft robotics, brain-computer interfaces, biorobotics, and mechatronics. He will be delivering his speech on facial expression rendering for high-fidelity robotic patients. So without taking time, I would like to hand over the control to Thilina. Thilina, over to you.
Yeah, thanks a lot, Damit. Can you hear me?
Yes, I can hear you.
Yeah, so let me share my screen.
Sure.
I might turn off my camera because to avoid any issues with the internet connection.
Sure.
Because I'm having like a bit of weak internet connection at the moment. You see?
Yes, we can.
You can see my screen as a full screen, right?
Yes.
Yeah, okay. Let me start then. Yeah, thanks again, Damit, for the nice introduction. Hello, everyone. I'm Thilina Lalitharatne from Imperial College London. First of all, I would like to thank the Center for Advanced Robotics, University of Moratuwa and Electrical Engineering Society of University of Moratuwa, and also the organizing committee of EECon 2021 for inviting me to this workshop. During this brief presentation, I will talk about facial expression rendering for RoboPatient, which is exactly what Dr. Shantha, Professor Shantha mentioned in his previous talk. So the majority of the research presented or research work presented in my talk are result of EPSRC funded project called RoboPatient. So this is a joint project between Imperial College London, the University of Cambridge, and University of Oxford, where our team is basically investigating how a soft robotic patient can be used to enhance the skills of medical examination of physician and as well as medical student. Among different branches of this project, I'm going to talk about my area of focus in this project, which is specifically aligned in rendering facial expression for robotic patients, and to investigate how doctors or medical students integrate different sensing modalities such as like visual, haptic, or vocal feedback during physical examination. To begin with, show how a doctor in domain of a simulated patient. As you can see, facial expression during primary medical education, primary examination, such as manual palpation, like in this video, is often used as a feedback modality to assess a range of medical hypotheses, or maybe during the diagnosis. When patient experience discomfort or pain due to palpation motion, as you can see in this video, they communicate their feelings and emotion through either verbal or non-verbal channels. So one of the non-verbal channel is facial expression. So by closely observing the facial expression of the patient, doctors can locate the area where the issue is, as well as he can regulate his palpation motion, especially the stiffness of the fingers, for example. Not only to detect any issues with the patient, but also to not to hurt the patient with this palpation motion. However, we know, as we know, learning to interpret this facial expression of a patient during medical examination or procedures is one of the difficult parts in medical training, because facial expression are so diverse. So it need time to get used to this different facial expression of diverse community. For example, a country like UK, like for example London, so you have like many different people around the world living in London, so it's quite challenging to identify or recognize different facial expression in the medical scenarios. So therefore, physical examination such as palpation, like in this video, requires years of experience to acquire skill, and also to basically recognize facial expression from patients. So that's the whole idea of my talks in today's presentation. So among different non-verbal communication methods, facial expression is considered as one of the powerful ways of communicating or providing feedback. So in fact, face is the most expressive areas of the body, which can produce around, it says 20,000 different facial expressions. So being able to receive or interpret facial expression accurately is an important ability during communication. So this is true, especially in medical field, as patients provide emotional cues during consultation, so which may be verbal or non-verbal. This figure shows an overview of the interaction between patient and examiner or a doctor. The interaction point you can see in these figures occur between phase 2 and phase 3, and also phase 5 and phase 1. So physician can learn some of the intrinsic factors from patient appearance, for example, or medical history. Some of the intrinsic factors that directly related to patient's health condition remain unknown. So physicians typically attempt to engage with experience and encoding the process by decoding and interpreting the verbal responses, but also combine with visual and haptic feedback to determine the unknown factors to make any diagnosis. So that's the basic process of how patient interact with the examiner during medical examination. So especially in medical, it's known that when properly interpret information related to pain experience, especially we are discussing pain expression of the patients experienced by patient conveyed to conveyed to the examiner by facial expression is sometimes more accurate than verbal responses. However, we know it is very challenging to interpret facial expression of one other person for training. For example, in this slide, so you can see different faces showing neutral and pain facial expression. So if I ask a simple question, rate the perceived pain level of these faces, we might see that each of you in this audience might rate these faces differently because some of the reasons for these differences may be due to your prior with people of certain ethnicity. For example, if you are familiar with East Asian people, so you know how their facial expression change, and if you are familiar with South Asian or maybe white, so you know how they pain, how they pain. So you have that prior knowledge, and then you can recognize their facial expression. However, these differences are critical in terms of medical examination, because if a doctor or medical student only diagnoses severity of pain, for example, it could result in mistreatment or even the mortality of the patient. Therefore, it's important for medical students to experience treating patients of different demographics and background, as misjudgment initial feedback due to objectivity could result in distrust between patient and health workers. But we already know the access to patients, especially in countries like UK or a similar diverse background, medical training is quite a bit of challenge. So these things motivated us to work this facial expression based facial expression during robotic patient. So in this my jet, so the whole idea is to basically render facial expression for a robotic patient. So the overview of the proposed robot patient with facial expression rendering is shown in this figure. The proposed robot patient consists of centralized soft organs such as liver. I think Thrishantha already showed some figures, and then those palpation forces and locations acquired from sensors. We have different set of sensors such as low sensors, torque sensors, and also related sensors. And then we use those sensor values to basically map the relevant facial expression in the robot patient. So I think we want to know the state of the art of this domain, because there were quite a lot of work was conducted in this similar area. So we searched prior work rendering in medical training. So photos from left side, you can see some of the commercially available medical training simulators for abdominal palpation training, and some of them had embedded sensors to record the and display palpation forces, but none of them consist of facial expression rendering. On the other hand, we found that there are other medical simulators with facial expression rendering, such as you can see from this top left-hand figure, pediatric hull, and also other simulators such as dental. However, it was evident that none of the available simulators with faces were able to change the diverse or the ethnicity or gender of the faces. And since majority of the faces are based on physical systems, a number of the facial expression are synthesized to these different simulators. Also, And then we explore the facial external rendering systems in other domains, because we can, if we have such systems in other domains such as social robotics, so we can directly use those systems in the medical field. So we did a study on literature study on that, and then we could classify the ecosystem into 3 classes as like physical, virtual, and hybrid. In physical systems, such as in this figure, you can see the faces are made using either electromechanical systems. So if you right hand top figures from left to right, we see that the appearance of the faces change from abstract to human-like faces, and also it concurrently increases the degree of freedom from low to high, and also the complexity. So nevertheless, even with these great details, now these faces are replicate diversity of faces due to gender ethnicity. And on the other, you can see from bottom left corner, fully virtual methods are capable of because basically synthesizing a virtual system. Those these 2D based virtual systems lacks the physical sense of agency compared to physical systems. Therefore, given the drawbacks in fully virtual and physical system, we found that hybrid systems can deliver accurate visual feedback with diverse faces, accuracy of diverse faces, adequate physicality. So these issues in existing solutions led us to develop a face called Morphace. To best of knowledge, this is the first time ever hybrid movable face capable of synthesizing faces of different gender and ethnicity proposed for medical training. So let me quickly show you of our developed system. So you can see this shows how our work. So to develop this design, we extract our principal console face database to design a 4-degree of freedom physical face with a set of motors, and then we use principal features, namely face height, position of the eyes, nose, and mouth, control, and to give the variation of the physical system, and high-level details such as skin color, for example, skin texture, and also the facial expressions are synthesized by or rendered by a virtual system, and then we use a miniature projector or level projector to project the hardware robot to get the different diverse faces. Yeah. Next slide. So as I said, to design this Morphace, we use a data push because we cannot just ad hocly design this face, because it has to be able to render different ethnicity and gender faces. So that we used 300 natural images of 3 ethnicities and 2 genders from a public facial image dataset called Chicago Face Dataset, which is open dataset. And then we extract facial landmarks of the facial image using our own custom program. And then we normalize the faces to have fixed face width, and then calculate 14 anthropometric measurements based on extract the landmarks. So we use image processing algorithm to extract these landmark at the beginning, and then we calculated these 14 metric facial measurements. Actually, we conducted a component analysis, or PCA, to identify key differing features between facial landmarks of this images set. So as you can see, the plot showing in right hand side show the results that we got from PCA. So first, we first choose species or principal with the percentage explain variance greater than 5 for our design,
and ultimately resulted in the cumulative variability of like 86%. So this whole process led us to select first 4 principal components for our analysis, and then we identified through this analysis, we identify face height, face width, or we're going to be visual width, position of eyes, nose, and mouth, nose height, mouth width, and mouth height as the principal features. So because these features represent the highest variance among all features. In parallel, we generate faces for each existing gender and rescale them to human faces. This figure shows the figure shown in bottom left corner shows the superimposed landmark plots of 6 average faces with actual facial dimension. We compare these results, PCA results earlier, and then we further reduce the number of principal features to 4 to reduce basically the complexity of the hardware. And then this allowed us ultimately to represent any given face of ethnicity and gender as a function of 3 function of face height and the portion of principal features of eyes, nose, and mouth, along with the y direction. And yeah, and then the physical system was designed using Fusion, and then some of the parts are made using 3D technologies with the PLA. And to add the different facial parts, we designed a modular linear data unit, which consists of simple RC servo and a tendon and linear guide. And so we able to move, namely eyes, nose, mouth, and lower jaw positions from these linear actuators. And from the analysis in previous set, we could trace the linear displacement of each face, and the simple relationship between linear motion to rotary motion to update the angles, and to basically control these different facial parts. And give you a bit on virtual system. So virtual system, we used to develop the virtual system. We used software called. So to generate virtual faces, we used an iterative mesh process. So I don't know whether you see the video. So it's quite difficult. So it's a video actually, the left bottom corner. So as shown in the figure and videos, we start the initial make of human model, and I change the facial features to match the make human virtual face with the respective average face we calculated in the earlier step, and then resultant set of faces to Blender, another software called Blender, and to render the final faces for projection. So in our current setup, we can mainly replicate pane facial expression. For that, we used 4 universal action units, or we simply in this area we call AUs, human face, which we represent for pane facial expression. So by wearing these 4 AUs, we were able to size different pane intensity of facial expression, and finally we integrate the physics we developed in the previous step and this virtual system to get the overall system, and to basically control and synchronize all 2 systems. Basically 2 systems, we used a custom-based MATLAB program, and yeah, and then we did a limited user study to test the effectiveness of the system. So these are some of the results that we got from that study. So in first study, we showed a set of natural faces to rendered by Prof, and then projected on flat surface without the face. And then from the users, we asked, so the parts asked a simple question: whether does this face look realistic or resemble a real person? So 64% strongly that looks realistic and real person.
And then in another study, or in the second study, the participants were asked to observe the set of randomly appearing faces, either no pain or 100%, as shown in this figure. Figure bottom right corner, sorry, bottom left corner. And then we asked them to rate the perceived pain intensity using scale of 0 to 10. And here we try to investigate the question as to whether the images we showed in this during our experiment, we just show the pain levels of 0, but we didn't the participants rather asked to rate the pain, and then the results were shown in this two plots. So we observed that there's a large percentage difference in perceived pain intensity between Asian and white participant for black male, white male, and Asian female, especially using morph face. And we also tested the effect of rendering methods between morph face and 2D virtual faces. And then the four out of 11 participants had a statistical significant difference in that aspect. So I mean, this was a preliminary study. So, but our preliminary study highlighted the potential use of morph face as a controllable, so robotic simulator to deliver quantifiable training, because we can basically quantify the facial expression in our setup, and to basically to give users on gender and ethnicity background of patient during physical examination. So yeah, so based on let me move to my next section talk. So based on this developed morph face, we extend the study to develop a first generation soft palpation or soft based palpation simulator, or we call it simply a robotic patient with facial expression. So to give you a bit of background, so these are some of the commercially available abdominal simulators, and there are quite a few research level simulators as well, as you can see from this bottom right hand figure. It is from Oxford Medical Simulation, which is a fully virtual reality based abdominal palpation simulation or training system. But what we noticed that was none of these systems are capable of rendering facial expression of different ethnicity and gender during their training process. But as I discussed in my previous slides, that is really important in medical training, because if you need to give these medical students or GPs proper training, we should consider about these different biases related to facial expression. So that motivated us to develop our first generation abdominal palpation simulators with facial expression. So these images shows how our proposed system look like. So this is actually very abstract level a system, which is no way looks like a human, to be honest. The oral system consists of morph face, which we developed in our previous step, and a soft silicon phantom to basically replicate the abdomen. And during palpation tasks on the abdomen phantom, trainees are presented with real-time visual feedback through pain expression, and based on the magnitude and portion of the applied palpation forces. But even though it doesn't look like really a human, but we try to arrange the overall system so that it can closely mimic the scenario of an actual doctor palpating on a patient's abdomen, as shown in this right-hand figure. So you can see like how it shows when you do a palpation examination. Yeah, I mean, so I think I don't know, maybe I can skip this part, but yeah, I will explain quickly about this. So at the beginning, we measure the palpation forces and the portion using a force sensor platform, which the force sensor platform had four sensors, and then we simply calculate the resultant and palpation location based on these four dorsal signals. And then more importantly, in order to map the palpation force and the position with the facial excision, we assume that the pain distribution across phantom, so across abdomen in a simulated case, to be normally distributed. So we basically model it as a Gaussian distribution as shown in this equation. So based on this assumption, the final pain intensity was estimated as a function of palpation force as well as the palpation position. So to validate our approach, the set of experiments we announced at the beginning. The main goal of this study goals of the study were to examine whether how gender and ethnicity of the patient and the participants influence the perception of pain from facial expression and error in locating abdominal pain. So this video shows our pilot experiment setup. So the trial sequence illustrated in the left figure. So at start, please be ready on the screen on the morph. And then ask the partner search maximum pain point by palpating the phantom, as you can see in this video. It's basically he or she can explore the phantoms of soft phantom, and then the task was to find the maximum pain point based on facial expression, and then just mark the located position using a single palpation point or single palpation action. Yeah. So you can see the experiment in this video. And then in this pilot study, 6 participants attended, and then these are some of the preliminary results that we got. So we observed that each subject shows different palpation force profiles for different gender and ethnicity background of morph. We also noticed that there's difference in 2 attempts, because we during our trials we did 2 attempts for each participant. So we noticed that there are differences in true trials. So, and also in general, subjects tend to gradually increase the force and then reduce it in the neighborhood of peak point. So it was hard to say this was due to pain excision or morph trigger any connection between, or empathic connection between the participant and the morph, but perhaps it could be. But so we consider it as an important or interesting question to address in our future studies. On the other hand, we also noticed that there's a difference in final peak localization errors across different gender and ethnicity background of the morph, especially different facial identities had significant effects on localization errors. And there was a significant interaction effects between subjects and the facial identities, especially in the region of within 10 millimeter region. So, but as I said, that this was a pilot study, so this we tested the system with fairly limited participants. So these results were not that conclusive to make any general conclusion, but these initial results highlighted the importance of facial. On the other hand, we extend this pilot study to an intervention study, because the preliminary results we got was interesting. Because the results highlights that there's a difference in perceived pain intensity with changes of facial identity. And also we noticed that this is also in line with human behavior psychological related literature as well. So these differences could be results from either biases or prior experience with pain expression with various ethnic and gender populations. So especially with the participants, their experience with other different gender ethnic people. Therefore, the study basically highlights the importance of training GPs or medical students to normalize these biases during medical examinations, such as abdominal palpation. So having this aim in mind, we designed an intervention experiment to study this effect of training with robot patient for normalizing these biases. So, but this is also still an ongoing work, but I thought it would be interesting to present a few slides about this work. So we designed these experiments and set up a protocol to test our proposed approach with physicians, GPs, and then medical students. And in our previous set of studies, we use only quite a few phases, but in the intervention, we basically increase the number of different facial identities so that it will give a generalized kind of phases of facial identities or facial expression for participants. So let me quickly explain how we plan this experiment. So in this experiment, the experiment task was simple and similar to what we did in the pilot study. The overall study consists of 3 blocks. In each trial of block 1, we asked the participant to find the maximum pain point by looking at respective facial expression. As this is where participants exposed to different facial identities and expression for the first time, we believe that if there's any biases, the data from block 1 should reflect this. And then in block 2, we introduce an intervention. So simply for this, in addition to facial expressions, we presented the pain intensity as a pain intensity scale as a bar adjacent to face during each trial. So I'll show you a video how we conducted this experiment. So our main hypothesis for this intervention was that participants learn the correlation between this pain intensity from this face as well as from this pain bar, and then apply the palpation force and then facial expression of different facial identities trial by trial, and ultimately learn an internal model to normalize these biases if there are any biases with them. So, and then finally, block 3 was simply to compare the results before the intervention. So we just we took during the experiment, GPs doing the experiment, and this video simply shows the experimental process. So it's for speed, like we have increased the speed of this video, but I think you can get the idea. So it has like 3 blocks, as I mentioned in my previous slide. Yeah. So and then these are some of the preliminary results that we got so far. So I mean, as I said, this is an ongoing work. So, but I thought to include this as this is something interesting. So based on brief analysis of the data recorded during experiment, we noticed that before intervention, so you can see from this block 1, that there are differences in palpation like the robot. And when we compare these variation with trials conducted after the intervention block, we saw that variation of average peak for palpation forces have become reduced across different facial identities, and this could be interpreted as a reduction of biases. So and also you can see how the participants change their peak palpation force with the number of trials. As you can see, like how, for example, the subject 2, the bottom panel, so she basically managed to learn this palpation behavior with the trial number of trials, as you can see from 0 to 10. But as I said, this is just ongoing work, so these results are not conclusive. But so we are conducting more studies on with GPs and medical students in coming weeks, and then hopefully we should be able to validate our hypothesis with these experiments. And in addition to palpation forces, we quickly analyze how the localization error changes within each block. This plot shows the results of 2 participants. Though we didn't see any significant differences in 2 cases between block 1 and block 3. But in both cases, in both scenarios, participants were able to estimate the pain point fairly accurate in both the cases. So this basically this also basically shows our hypothesis of our previous thinking. So this is what I'm doing at the moment to basically to extend this study to basically get the input from medical students and GPs to basically test our hypothesis. Yeah, so do I have time? I think yes. So yeah, I will quickly go through this. So there will be another 3-4 slides. So so this is another study that I would like to talk about during this presentation. So this is an ongoing study, another ongoing study that we are conducting at University of Cambridge in a slightly different project. We want to explore how a robotic patient with facial expression can be used in teleoperated or remote palpation schemes. So earlier we had a robotic patient, but in this case, we want to use the robotic patient with a teleoperated system. So because we know teleoperated systems and robotics have been part of the healthcare system for nearly like over 20 years. Robotics platform have been already used widely in several fields as or MIS and endoscopic innovation. Similarly, there have been a number of attempts of developing solutions for remote palpation. For example, you can see these existing systems in this slide. Many private have been focused on providing only haptic feedback during remote palpation. So, and some studies adopted strategy of showing like tactile information, for example, tactile information recorded remote 10, and then those information rendered using color matrix, for example. So those are the existing methods that researchers use in this domain. However, based on our previous experience, it's safe to argue that these alternative visual systems are not intuitive as facial expression during palpation examination, because doctors or medical students are quite used to this facial expression rather than other visual or visual display methods. So in this project, we want to explore the possibility of using facial expression as a feedback modality in remote palpation application. So we go the two sides. So our proposed system consists of a robot patient, which we developed in our previous studies, and then basically to render facial expression, and a robot doctor basically realized using UR5 robotic manipulator, and it has a tactile sensor array basically to detect any sensor information of any soft phantom which is placed under the robot near the robot doctor side. So because one of the motivation for this study was we know that facial expression are familiar to human, whereas alternative systems are not. So especially if you want to show let's say stiffness changes or haptic information using a haptic display such as a color matrix, it would be more intuitive to show these variation using facial expression, because humans are basically human visual brain is able to efficiently decode signals from face and to enable adaptive actions. So the scientific question that we tried to explore in this study, whether we can use facial expression as visual feedback during remote palpation tasks, such as finding a hard nodule or a tumor against other visual feedback. And also we want to explore the notion that the face can be act as a data compressor during communication. For example, as you can see from this slide figure, the sender encodes a message, "I feel happy," as a form of information such as facial expression, simply by simple smile. and then transmit across communication channel and the incoming, and he or she uses his or her prior knowledge to extract the task relevant features and perform an interpretation. Typical result in a sufficiently accurate reconstruction of the message. So in this case, he is happy. So this simple approach that we were interested in, this simple approach, because I feel happy. Kind of complex message. This is in this case it is simple, but you can send a complex message and encode that in a facial expression, and you can send it to another person, and then that person can understand using that emotion using your facial expression. That's the whole idea of this work. So as you can see, our overall system consists of a RoboPatient and a RoboDoctor. To implement the remote connection, we use UDP connection, simple internet connection. And then we use a custom developed capacitive multi-sense array to measure the stiffness changes, manipulate palpate, when manipulated palpate on a phantom. So this is the overall structure of our proposed system. And then this brief video shows how the experiment task should look like during the study. So during experiment, we asked the participant to localize a hard nodule embedded in a soft phantom at the RoboDoctor side based on facial expression feedback of the RoboPatient. So in this pilot study, we compare our proposed approach using RoboPatient facial expression against the other visual approach as we use in this video. You can see a color matrix. So basically, we map the tactile array data to the color map, and then we compare the localization accuracy or ability with the face. So it was a very simple experiment. And this figure shows data captured during a trial. So as you can see, how platform captures the user inputs, and then how, based on that inputs, how the robots move from this left-hand figure. And then right-hand side figure shows a graphical comparison of two visual systems tested in study. So as you can see, the same palpation motion on a hard nodule. You can see the phase variation, and also you can see how the tactile display of tactile matrix changes, and how the phase change when robot palpate on a silicon or soft area. And then we conduct a pilot study with the 5 naive participants, and then this slide show a preliminary results we got. So we analyze the hard nodule localization accuracy for both the approaches, and then we observed that 4 out of 5 participants were able to localize the hard nodule more accurately with the facial expression feedback compared to color matrix. So you can see from this, I don't know whether you can see this cross clearly. Yeah, maybe I'll more explanation to this. So this bar plot shows the summary of the localization accuracy during 2 experiments. So as you can see, 4 out of 5 participants were able to accurately detect the hard nodules using Morpheus with compared to matrix. In addition, we compare the localization error for both the approaches. All subjects managed to estimate the portion of correctly identified nodules within 30 millimeter accuracy. So you can see from this table. So and comparison between variation of palpation forces across all trials shows some trends, but unfortunately, we didn't have a lot of participants, so we couldn't really generalize the results. But we saw some trends that we can explain some of these participant behaviors during these 2 approaches. And more importantly, 4 out of 5 participants mentioned that they found it found it easy to find nodules using facial expression as compared to color matrix, because in the case of color matrix, they had to concentrate on color changes, double color changes, as well as the pixel changes. So the results from this simple study is interesting because it basically shows that the proposed approach of showing these feedback using facial expression work, but we need further studies to basically test our hypothesis that these alternatives, these facial expression systems are better with alternative other visual systems. So yeah, so all in all, we show that face or facial expressions during medical examinations are important, and we hope that as a medical examination and as well as training will open up a new direction in medical robotic field, because as far as we know, this is the first time that a group is working on rendering facial expression, especially diverse facial expression for medical training and medical simulation. Yeah, I think that's basically some of my brief talk, and I hope you have gained something out of my talk, and thank you very much for your kind attention.
Thank you very much, Dr. Thilina. Now the floor is open to questions. I have few questions that came up from the chat. The first question, Thilina, is without having hardware system like yours, would it be possible to do the same thing with the augmented reality or virtual reality approach?
Yeah, that's I think a really good question. I mean, that question was asked by many people, especially when we try to submit one of our papers. Yeah, that's exactly true. So virtual reality or augmented reality is another dimension to this approach. But what we really what we learn from several studies, especially in psychology and human behavior related studies, that physicality is one of the important things, because in virtual system or augmented reality system, the render systems are virtual, right? So you don't really feel you have like a physical system. So let's say you have a physical robot somewhere, and then you have like another system which can render the same thing, but in a virtual system, the sense of agency is totally different. So that was our argument to basically propose this physical but rather hybrid physical plus virtual based approach for this robot patient. But of course, as what you said, of course, we can have alternative systems such as AR or VR based approaches for same thing. Yeah, that could be.
Thank you. Another question is, how is this robotics approach welcomed by the physicians? Do they like it?
Yeah, that's a good question. As I said, so we are conducting an ongoing study with this system with GPs from University of Oxford. Actually, I was in University of Oxford yesterday for one of the trials. So we at this moment we have conducted experiments with around how many 9 GPs. Yeah, the response were amazing. I mean, one of their question was like this whole system, even though we consider this as a robot patient, it doesn't look like a robot, because it's in an abstract level, right? So
yes.
So that was one of their kind of complaint, but still they really value the contribution, because this is pretty new to the field, because rendering facial expression is pretty new to the field, and that will really helpful them to basically normalize their biases during these palpation traits, especially palpation training. So that's some of the comments from GPs. But we need to do further studies with GPs, closely working with GPs to basically validate the overall system. Yeah.
Thank you. Another one question that I have is, in training and so robots sort of information or in University of Moratuwa, what sort of points that we can take from your research that might be helpful to develop the research culture in Sri Lanka, biomedical field?
Yeah, good question. Because I was with Department of Mechanical Engineering, I mean, with you and all my colleagues during last 10 years, right? I know how the university system works. So the major difference I noticed when I worked with Trish, so in Imperial and Cambridge, I mean, as he talked in his talk during Q&A session as well. So it's better to work on fundamental questions rather than like more application towards questions in our research. But one of the major issues is budget. So we need quite a lot of budget, especially if you're planning to robotics or high-end related research. But as Professor Chan suggested, like if you really trying to tackle industrial questions, especially related to particular country, and then try to identify fundamental questions like the scientific question more, and then try to address these things. I think that's the way forward, because I mean, we have seen like a lot of research, especially I know, I mean, electrical department, electronics, mechanical, I mean, other departments as well, computer. So we in Moratuwa, we do a lot of good research, but I think at least some of us, we need to focus on fundamental research, I would say. So that was my personal opinion. I mean, what I found as a difference between like British universities and Sri Lanka. But of course, yeah, that's a good question.
Thank you. I think that's all the time that we have for this session. And before we wind up this session, I would like to thank Thilina and Prof. Thrishantha for giving us this valuable speech and taking your time to come and work with us. But the official vote of thanks will be coming soon. And for that, I would like to welcome Dr. Prasad Bagduage to give the official vote of thanks. And I give you over to you, Prasad.
Thank you, Damit. So on behalf of the organizing committee of EECon 2021, I take this opportunity to thank and Thilina Lalitharatne for conducting this useful workshop on soft robotics biomedical. So very much. And thank you, Dr. Damitha, for coordinating the workshop as a collaborative event with Center of Advanced Robotics of University of Moratuwa and IEEE RA Sri Lanka chapter. Finally, thank all participants. I hope with the workshop. Thank you much.
Thank you.
I think we should take up there, right? Ravi?
Yes. Thank you, Dr. Prasad, and that marks the end of the soft robotic workshop session for biomedical applications of EECon 2021. Before we move on any further, I humbly request all of you to turn on your video camera for a moment. Thank you for your collaboration. Stan and Sami want to do for the final events of the EECon 2021. Thank you.
Thank you, Ravi. After having 2 brilliant keynote deliveries, 4 technical sessions, and a robotics workshop, we have arrived at the concluding session and award ceremony of the EECon 2021. Finally, I would like to cordially invite the Dean, Faculty of Engineering, University of Moratuwa, Professor Nalin Wickramaratne to address the EECon 2021 gathering. The floor is yours, sir.
Thank you. Thank you, Swamini. Thank you, all of the participants. Good evening to all of you. And of course, it's a pleasure for me to say a few words at the concluding session of this Electrical Engineering Conference, or EECon 2021. Simply because I was at the Department of Electrical Engineering when the inception idea of Electrical Engineering Conference came up, maybe some 10 years back, I can't remember when. The idea was to give a chance to our own students to showcase their research skills, and also to disseminate knowledge and to encourage discussion regarding their own research results. Electrical power engineering and its applications. And conducted the original idea of Electrical Engineering Conference within the bounds of the Electrical Engineering Department quite a few years. And then we thought that since we have been successful, why not make it broader, not subject-wise. We wanted to keep the focus on electrical engineering power and its applications, and we wanted to make it open for whole country so that everybody can submit their papers. And later on, of course, a few years again later, we thought now we are mature now. We will not go for a international conference. So yes, with the technical sponsorship of now we have had this particular EECon conference for, I think it's the 4th time that we are having it, and it's the first time online that we are having due to the current situation of the world. But still, you have made a very good contribution. I am sure you had a successful conclusion to this very wonderful conference by now. Everybody contributed. I want to particularly, I am very happy to see that we have received more than 50 submissions from 16 different establishments. So that means 15 different institutions outside the University of Moratuwa, including China and India. And all the papers have been by double-blind process, and less than 50% of the papers have been selected. So I congratulate for keeping a very good record on the standards of the conference. And at the same time, I must thank our keynote speakers, Dr. Dinesh Gurusingh, who delivered digital real-time simulation on power and energy systems, a very important topic these days. And also keynote speaker number 2, Professor Kai Song, as a professor from Tsinghua University, China, delivering his talk on power conversion technology for renewable energy systems integrated into medium voltage DC grids. And then again, of course, the workshop participants and the resource persons for the workshop, Professor Thrishantha Nanayakkara and Dr. Thilina Lalitharatne, thank you very much for your efforts. And of course, finally, I want to thank our honorary chairs, then particularly very big thank to General Dr. Mrs. Tushara. It's not easy to organize this kind of a conference, even though it's one of the smallest conference in the university, but still it's a very big responsibility. So thank you very much, Dr. Tushara. Then Program Chair, Dr. W.D. Prasad, and Dr. Thilina Lalitharatne, thank you very much for publication chair, Dr. Harsha Bacon. So thank you, all of you. And then everybody in the committee, track chairs, all the track chairs, and all the distinguished guests and our own staff in the technical program committee and reviewers. So without your help, of course, we could not have concluded the conference this successfully. So finally, I want to thank all the participants, all the authors, and also those who will receive Best Paper Awards today. Thank you very much for your patronizing our EECon conference. And finally, on behalf of the University of Moratuwa, particularly our Faculty of Engineering, a big thank to all of you. Thank you.
Thank you, dear sir, for your remarks. Next, without any further ado, let's move on to the award ceremony. To chair the award, General Chair and our Program Chair of EECon 2021, Dr. Thilina Lalitharatne and Dr. W.D. Prasad. Over to you, sir, and madam.
Good afternoon. So thank you very much. First, let me to explain how we selected the best papers. So in this conference, EECon 2021, we received more than 50 papers, and our publication chairs, with the help of track chairs and all the reviewers, they managed to get at least 3 reviews per each paper. So first, what initially, from the accepted papers, the papers were selected, which are nominated for Best Paper Award in each session. We had 4 sessions: Power Systems, Energy, Power Electronics, and Robotics. So based on the review score, those papers were nominated. And then during the presentations, session chairs evaluated those presentations based on the quality of the presentations, contributions, and etc. And they ranked those presentations, those papers. Then eventually, the best paper in each session was selected on a weighted average of 60% for the review score and 40% for the marks assigned by the session chairs. So that is how the best paper in each session was selected. And so let me to announce the best papers in each session. The first session, session number 1.1, which is Power Systems. So the best paper award goes to Optimum Wind Turbine Design and Analysis to Harvest Wind Energy from Fast Moving Vehicles on Highways. Authors are Nanayakkara Vidyalankara, Nilanga Jayavikrama, Dilsh and Velmanikam Logishan. So congratulations. Second, it is a session number 1.2, Energy Systems and Smart Technologies. The best paper award goes to paper title, Performance Evaluation of a Hybrid Dual-Axis Solar Tracking System. Authors are Kitma Vidana Patirana, Hansi Kumara Peli, Dineshi Marasingha, Dulini Amarasingha, Joseph Rohlus. In session number 1 is Power Electronics Applications. The best paper award goes to the paper title, Hardware and Control Design of a Novel 3-Phase Quick-Tie Inverter System. The authors are J.P. Karunadasa, Sandali Savindi, Nimesha Kumara, and Hema Jayasuriya. Then the 4th session, which is Robotics and Intelligent Systems. The best paper award goes to the paper title, Object Identification Using Support Vector Regression for Haptic Object Reconstruction. Authors are Pravina Vimarshani Devapura, Malit Jayawarthana, Harsha Beko. So congratulations, all the Best Paper Award winners. Thank you.
Yes, I would like to congratulate all the award winners, and also thank you very much for all the participants for the research by publishing their research papers, by selecting our conference to present their interesting research findings. And to conclude the session, I would like to invite the program chair, Dr. W.D. Prasad, to deliver a vote of thanks.
Thank you, Dr. Tushara. Once again, good afternoon, all of you. We have now come to the end of the third International Electrical Engineering Conference, EECon 2021. This is the first time that the conference was conducted entirely on online mode. I believe that we could successfully conduct the conference. That success was achieved with the help of many personnel. So thus, as the program chair of this conference, it's my duty to appreciate the hard work of all the colleagues behind the scene and also acknowledge the sponsorships received. First, I offer my sincere gratitude to all the sponsors, IEEE Sri Lanka section, IEEE Power and Energy Society Sri Lanka chapter, IEEE Robotics and Automation Society Sri Lanka chapter, IEEE Power Electronics Society Sri Lanka chapter, and engineering. Further, the financial assistance provided by the Amity Power Consultants was also appreciated. Then I am reminding the two keynote speakers, Dr. Dinesh Gurusingha and Professor Kai San, for accepting our invitation and delivering the keynote speeches, which were very valuable. Then we had an interesting workshop on soft robotics for biomedical applications. I am very thankful to Professor Chandima and Dr. Damit Chaturanga, who were very supportive in organizing this workshop, and also the two resource persons, Professor Thrishantha Nanayakkara and Dr. Thilina Lalitharatne. In this conference, there were 4 technical sessions. All the session chairs, Dr. Amila Vikramasinghe, Dr. Asanka Rodrigo, Professor Andrew Vijaypala, Dr. Vijay Konbanda, Dr. Ranjit Leenapathirana, Dr. Vidura Jayasuriya, Dr. Peshala Jayasekara, and Dr. Kasun Prasanga. Thank you very much for accepting our invitation to be the session chairs and help us in conducting the sessions smoothly. With that, I am taking this opportunity to remind and acknowledge all who involved in the review process. As I told, we received over 50 papers. It was challenging to get at least 3 reviews per each paper. I am reminding all the and all review process to get this done, and thank you much. Also, I'm taking this opportunity to thank all the staff members of the Department of Electrical Engineering, University of Moratuwa, including Professor Nalini Vikramarachchi, the Dean of the Faculty of Engineering, and Professor Udayanga Hemapala, the head of the department. All of them were very helpful to make this event a success. Now I am taking this opportunity to appreciate the hard work of all the members in the organizing committee of EECon 2021. Thank you, Dr. Tushara Damayanti, the General Chair of the conference and the President of ESOC, for guiding us always to this conference. I am reminding all committee members, Dr. Harsha, Publication Chair, Dr. Logi, Publication Co-Chair, Dr. Saranga, Financial Chair, and Dr. Rasara, Local Organizing Chair. During this pandemic situation, actually, we could not conduct any meetings physically, rather we managed all things virtually. So thank you very much. Then it is my pleasure to remind Ms. Naveen and Ms. Gitmi, the conference secretaries, who handled many of the related work. Finally, all the students from ESOC, thank you very much for the support extended. I think this is the very first time that you all attended an international conference. Sadly, it is in online mode. Anyway, the all committee members humbly appreciate your hard work and thank you very much, because without that commitment, this work could not be successfully completed. I think I didn't miss anyone who involved in this journey. Apology, everyone. Finally, thank you very much again, and we will again in here with both IEEE and EECon. Yes, thank you very much.
Thank you, dear sir. With that, we hereby the conclusion of EECon 2021, the third international conference organized by the Electrical Engineering Society of University of Moratuwa.
With the hope of bringing you another such conference in the future, we are signing off. So let's sorry, my connection issue. Let's conclude our EECon 2021 with a high note and the hope of having another session in 2 years' time. Good night and stay safe.